Super, thank you, Fraser. So I'll be talking about Obsidian, which is a language for programming smart contracts, which tries to make those smart contracts safer, but also provide usability for programmers who work on it. So this is work done in collaboration with my former grad student, Michael Koblenz, now a professor at UC San Diego, as well as my colleagues Josh Sunshine and Brad Myers. And it was sponsored by both the Department of Defense and Ripple. Smart contracts in Obsidian. I think probably everyone knows about smart contracts in this group, but we are trying to enable people to write down how transactions between untrusted parties should work, make them tamper resistant. But unfortunately, when we do this, smart contracts are written by humans. We often make mistakes, right? And so smart contracts can be buggy. We can lose lots of virtual currency, and we have lost lots of virtual currency in the past through bugs. We'd like to avoid making those mistakes. So Obsidian is supposed to be a safer smart contract language. Okay, we're not necessarily trying to specify and verify everything, but we'd like to put up some guardrails to avoid some common kinds of errors that get made in these systems. In particular, we're applying two technologies. One is type state, been developed for a while, including in my group. It mitigates misuse bugs where you perhaps don't obey the intended ordering of calls to a contract. The DAO bug from a few years ago was one example of that. Linearity is another technology we're applying. It mitigates lost asset bugs by making sure that you can't create or destroy currency. Or lose track of it in this case. And so the research goals are safety through these mechanisms like type state and linearity. But the new element really is using HCI techniques in addition to traditional programming language methods to make sure that these approaches we're using are not just sound but are usable by programmers. So to give you a little bit of an example, it's always fun to show a smart contract language. This is Obsidian. Here I'm creating a contract for a tiny vending machine. Illustrative example, of course, to keep it simple. But our tiny vending machine is a contract. It has some coins in a coin bin. So this is just like a field. But note that its type describes that the coins are owned. So those coins are owned by this vending machine. No one else can access them or use them. We have type state, and so we have two different states of our machine. In the full state, we have an inventory, which is one piece of candy. As I said, it is a tiny machine. And then we have the empty state. And of course, we can transition between those. And so one logical transition is when we buy something from the tiny vending machine, then we do the buy transaction. And you notice the notation here, the tiny vending machine goes from being full to being empty, right? Because it's delivering the candy. We pass in a coin, and from the perspective of the caller, the coin starts out as owned by the caller, and it ends not owned by the caller anymore, right? Because it'll be now owned by the vending machine. And then we'll return candy, which will be owned by the caller, right? So these annotations that talk about who owns resources like coins and candy and what the state of things are, those are from the perspective of the client to make it sort of readable and understandable from the client's perspective. Okay, and we can of course implement this, and we can verify our implementation to make sure it meets these criteria of ownership and type state. So in this case, we'll deposit the coin in the coin bin, which transfers ownership from the variable C into the data in the coin bin. We'll take our candy out of the inventory, put it in a result variable. We transition to empty, and then we return the result. Notice that if we had, for example, forgotten to take the candy out of the inventory, for example, we'd be losing track of a resource, candy in this case, and our type system would tell us, oh, you have an owned resource that disappeared, you can't do that. So it's able to be helpful in this way. So how did we actually make this language usable? Well, we applied a methodology, including a bunch of kind of formative and summative user studies. But I want to give you a little picture. Since the talk is short, I'm going to focus on just the results that we got out of this. And I think they're kind of interesting for language design point of view and for type systems, because there hasn't been a lot of work on exploring usability. And sometimes people think, oh, HCI stuff, that's for interfaces, right? Pretty pictures, and maybe for languages, that's keywords. But actually, it's more than keywords. It's also about kind of your mental model and how you manipulate structures. So, for example, our initial design for combining state and ownership was to have orthogonal representations of ownership and type state, right? So if we have a tiny vending machine and we want to keep track of its state full, then we say that it's a full vending machine. Maybe it'll transition to empty in the future, but also we own it, and that's important because we can only track the state of things that we own. There's a long-standing problem in tracking the state of things that alias each other in programming languages, right? It's like one of the super hard problems in programming languages. So this separation, kind of ownership on the one side and type state on the other, is sort of conceptually clean, and to our knowledge, all prior systems that had both of these concepts separated them, including some of our prior work. But we found in the user studies that there was actually a disadvantage to this design. So one user said, I haven't seen types that complex in an actual language enforced at compile time before. Okay, this is just a sample quote, but it's like it characterizes the thing that we saw, right? Which is that people were in fact confused by this, and it was difficult to teach them and make them really understand what was going on, right? Now, there's always training, right? We could have sat these people down in a classroom and taught them some lectures and so on. And I'm sure we could teach competent programmers to do this over time. But I think it speaks to the accessibility, right? How quickly can you communicate something? If people look at a notation, do they understand what it means right away, or can they guess correctly what it means based on the notation? So I think it does affect how quickly people can learn, and maybe the misconceptions that they have. And we know misconceptions lead to bugs. So it turns out in this case, this separation between the dimensions of ownership and state was not actually needed. And the reason is that these are semantically tied, right? You can only track the state of owned things. So if you know something about the type state of something, that actually implies ownership. Okay? Now there are corner cases where you can get around this, and so this, by combining these, which is what we eventually did, we do restrict our expressiveness a little bit, but it's really very corner cases where this affects things. And it turned out to make things much easier in terms of teaching participants, right? And so you'll see later on we did a study on usability, but basically the only way we were able to do that study was because we were able to teach the language to people quickly and get them to understand it. And so this is one of many kind of things that we did. And I want to emphasize that, first of all, there's an interesting insight here that you can refactor technical ideas just to present them in a different way. It's still a sound type system, but it gives the user a simpler conceptual model. And secondly, this, it is a matter of notation, but it does affect some things, right? It affects we have a construct for, asserting the type state of something in a temporary way. And this affects the way, like testing a type state and then using that knowledge briefly. And so it's like a locking construct. We gain temporary ownership of something that's otherwise shared. So this choice actually affects the construct, the way that language constructs like that are designed. And that then affects the formalization and could potentially affect the properties. So it deals with it gets into a lot of the things that we deal with when we design languages and type systems. Okay, a couple other design changes. One was making permission changes explicit. Our original design, if you're passing an asset to a contract method, you would call it owned if the asset is kept by the caller and borrowed if the asset is returned, right? Own, pass it and return it. But we got feedback from users that this is confusing. When I annotate this as owned, I don't know if I'm making the variable owned or if I'm transferring ownership, right? These are two different concepts. And we found it was actually clearer if our notation made change explicit, right? So that's where we came up with this arrow notation that an asset goes from owned to unowned, and then you can just see in the signature when something changes, right? So I think, again, the notation matched the user's conceptual model better. Now this is a case where prior systems, some had taken the choice of kind of a change from one thing to another, and some had used abstractions like borrowed. You will find both of these choices in the literature. And so now we know which one is more usable, right? At least from the qualitative studies that we did. So I think that's a useful thing, and something that other people in working on linear type systems could use. A last design change had to do with initializing and transferring assets. I'm not going to go through this in a lot of detail, but we looked at kind of a functional or constructor-based way of changing state, as well as a kind of assignment, assign things into the new state and then do an atomic change at the end. And people like the latter one. This is an interesting choice because I think the preferences here might be tied to people's prior experience, right? Most of the programmers in the world are imperative programmers, for better or for worse. So that affected maybe this choice. But maybe if we trained more people to functional programming, that might have gone the other way. So it's an interesting thing to look at there. All right, does it actually work? So everything I did so far was validated with qualitative studies. 1 or 2 users kind of looking at a handful of users, not necessarily 1 or 2, but looking at qualitative information more than quantitative. At the end, we wanted to see, in a quantitative study, does this actually help? So we got 2 studies. One was a usability study. We had 6 participants, and the basic question here was, can we consistently teach people to complete a task in Obsidian? And in fact, within about an hour and a half of training, which we think is not too bad for a brand new language with some weird type system constructs, people could be successful with this. We also did a randomized controlled trial. This is more the experiment, and we compared Solidity to Obsidian, and our success rate in completing the task correctly went up from 2 out of 10 to 7 out of 10 participants, which is a pretty big rise. The ones who didn't complete, in most cases, they completed, but they had a bug if they failed, right? So we didn't actually slow people down much. We still had 8 out of 10 people complete versus 9 out of 10 in the Solidity condition. But Solidity, in the Solidity case, 7 people had a bug that lost money, right? Transferring money is actually kind of tricky in Solidity. I'm sure a bunch of people are familiar with those challenges. And so, we just, the linear type system and so on, were able to catch most of those bugs. We did not catch all bugs, right? Because we don't have full functional specifications here. One person had a bug where they refunded money to the wrong party. Okay, so types are incomplete, but they can help a lot, and I think it's nice to see that here. We also did some interesting case studies. One was a case study in parametric insurance with the World Bank. The idea here is if you have people in a developing country, you may not have a lot of trust in institutions. So this is a place where smart contracts and blockchains could actually help. And with parametric insurance, instead of having an inspector come and look at your crops and see if they failed and assess the damage, you just get a payout versus the weather, right? So if it hails and it damages your crops, you're going to get a payoff for the hail, not necessarily for the crop damage, but for you, you got paid off either way, right? So it's a nice solution to this domain. We did a case study, again, looking at Obsidian versus Solidity. You can see them side by side. Not going to ask you to read all this code, but you can see a few highlights. Obsidian is actually shorter. Partly that's because we're able to avoid, basically the checks that you're calling the contract in the right place are built into the contract. So a higher level of abstraction has a lot of benefits. There's a lot of manual state tracking in the Solidity policy, which we were able to just roll into our state abstractions. There's all these state checks that are there, gumming things up. And in Solidity, you have to basically update your variables in every state the way that things worked out. So we were able to simplify with our type state abstractions. Okay, so overall, we explored adding 2 type system constructs to a smart contract language. that guarantees that certain kinds of exploits or vulnerabilities can't happen. I think the takeaway I come out from this is that not only is designing type systems hard, but designing usable type systems is hard, right? And historically, some of the decisions we make are poor if we don't study these things, including some of my prior decisions, right? So we learned some things from this study. And I think by combining programming language theory with the HCI techniques, we can get the best of both. We can do validation with user experiments, with proofs, with case studies, and perhaps other things as well. We're now looking at richer kinds of specifications. One of our projects is applying a kind of gradual approach to verification that makes verification more incremental and mixes static and dynamic checking. And I think it's an interesting thing to explore in this domain because we care a lot about correctness. So with that, I'm happy to take questions. Thanks.
Very nice talk. Can you tell a little bit about can you say a little bit about the participants? So did they have experience doing smart contract programming, or did they have experience programming at all? Like maybe they knew Rust, or I don't know.
Yeah, no, great question. And that is very important because that affects what you can conclude from our study. So we had, we chose people who had a fair amount of experience. There were some students in the mix, but they had usually 5 years of programming. We also gave a Java study, so they weren't specifically familiar with smart contract programming languages, but they were all pretty good at Java. Got at least 4 out of 5 on a test of kind of the language lawyer sorts of questions. So they were, I think, pretty qualified people. But we had to teach them from scratch both Solidity for the Solidity case and Obsidian for the Obsidian case. And the tutorials were similar, but as similar as we could make them given the different models of the two languages.
So I really love the way you're using usability to explore language design and the fact that you're actually evaluating on humans. That's hard. So,
it is.
Wonderful. One thing I'm wondering about, as a fellow designer of fancy type systems, I've always found that a big challenge is giving users the right kind of diagnostic report so that they can identify when they're making, what their mistake is. So they're confronted with a type system they don't maybe completely understand. They write code, they get an error report, and they don't know how to get from there to fixing the bug. And I'm just curious what your experience was with that process, like in Obsidian. Did you spend? Was it a challenge to design the right feedback, or yeah?
That's a great question. I wish Michael Koblenz was here because he's the one who did that hard work with the users. He probably would have an answer to that. I do know I agree it's a very important issue, and I'm actually working on that with another student in a slightly different context. We're looking at I love it when concept just like flies out of your brain. Refinement types in liquid Haskell, liquid types. So we're looking at liquid types in error messages, it's a notoriously challenging type system, trying to make those easier to use. So stay tuned maybe for results on that. Yeah, it's a big question for these systems. Thanks.
Great talk. So I wonder if you have thoughts about mixing Obsidian with Solidity. And the reason I'm asking that is because, look, I mean, not all smart contracts are made equal. There is a lot of few. There's a handful, let's say, that initial critical, where people can apply, let's say, verification techniques to the core of Obsidian, the core of Uniswap, but not, let's say, much more broadly. So what are your thoughts? I mean, can we have certain things in Obsidian and then a bunch of others that are in Solidity?
Yeah, that's a great question. I think it's important that we be able to do this. Our initial implementation of Obsidian was actually targeted at Hyperledger, not Solidity. We have since targeted solidity, but it's a little more difficult because we actually built Obsidian as a garbage collected language, and the Solidity blockchain doesn't have garbage collection. So there was an interesting side project right in there, actually. Yeah, I think, you know, in general, we'd like, you know, contracts written in different languages to talk with one another. And I think it's also interesting to think about how do you port constructs like type state and linearity, which are specification constructs, with, you know, whatever specification constructs might exist in some other language. Maybe you have pre and post conditions, for example. So, yeah, good question. I don't have a lot to say about it, except I think it's a good direction for future work.